a review. So basically, we have the function of AC machines, generator versus motors. So basic principles associated with the generation motoring action is really based on the two very basic formulas that we talked about at the beginning of this course. The two major types of AC machines were the synchronous machines and induction machines. The synchronous machines are the machines that have constant rotational speed, or we designed them to have a constant rotational speed in either generating or motoring mode. But the induction machines are not like that. So in the induction machines, the rotational speed of the machine really depends on basically how much load is there in the motoring action. For example, if you put more load, then the speed of the motor would change. So we'll deal with that when we talk about induction machines later. But for synchronous machine, keep that in mind. Under steady state conditions, we want to have a constant speed. The field in AC machines are located on the rotor. And we provided the fundamentals associated with three-phase synchronous and induction machines in this chapter. So the flux distribution could be very complicated, but the way that we want basically the flux to be distributed in these machines are based on a sinusoidal pattern. So in general, an AC machine with cylindrical or non-salient pole rotor is like this. You have uniform air gap between the stator. So the outer basically portion is associated with the stator. The inner portion is associated with the rotor. As you can see, there is uniform basically distance or space between the rotor and the stator. That's why we call this non-salient or round rotor. And here are the armature basically windings that have been embedded inside the stator. Here we have the same type of construction, except for the fact that the rotor is not non-salient, it's salient, in other words. So it means that there would be a non-uniform distance between the rotor and stator in terms of the air gap. Here, air gap is less. Here, air gap is more. Okay. The flux path would be designed in these motors in a way that the direction of the magnetic field would be always coming out basically like this in a 90 degrees angle with respect to the stator, as you can see. So it's coming out of the rotor, going into the stator on a 90 degree basically fashion. So design would be based on that. We talked about rotating magnetic field, which was talking about like if you have a permanent magnet in here, which you are rotating with a constant speed. The same effect can be made through having some sinusoidal currents existing on the stator in three different phases. So they would produce basically three magnetic fields, BA, BB, BC, associated with the three phases. But their interaction between these, considering the fact that each of these windings are having sinusoidal currents in them, the combined interaction between all of that would be as if there is a rotating magnetic field, just like the one that we have here on the right-hand side. So this is very important in the construction of AC machines. We could have more than two poles. So in this one, we have a four-pole machine, and its associated stator winding. There is a pole pitch. Pole pitch is the distance or the angular distance between the north and its adjacent south pole. This pole pitch is always 180 degrees in electrical, basically degrees. But depending on how many poles in the machine we have, the number of basically poles would determine what would be the pole pitch in a four-pole machine, for example. In a four-pole machine, the pole pitch would be 90 mechanical degrees, but in 180 electrical degrees, if that makes sense. And this would determine the electrical displacement versus mechanical displacement, and electrical speed versus mechanical speed, which would be related based on P over 2, where P is the number of poles in the machine. All right, so we talked about this simple design, but this simple design that has a north pole and a south pole would have the maximum, basically, field at this point and the minimum field at this point, and we would have 0 here. So in between, the distribution of the magnetic field is not really sinusoidal. By the design in electric machines, we want to do it in a way that we want to design basically the field in a way that its distribution would be sinusoidal, which means that based on if you're sitting in here and if you rotate with respect of the alpha angle around this basically stator, we want to see the minimum here, the maximum in here, and we want to become zero here and then minimum here and then zero again, based on a sinusoidal pattern, not based on any other form of pattern. We want basically, when we move from here to here, we want to go from zero to maximum in a sinusoidal fashion, if that makes sense. And then come back to zero, go to minimum, come back to zero again in a sinusoidal fashion. This is hard to do, but those who design these machines make it in a way that it would be kind of similar to that. So this is the ideal, basically, way that we want it, but really in practice, it really depends on how many conductors we should put in every slot so that we can get kind of similar to that sinusoidal, but not exactly. So we looked at the basics for inducing voltage in a rotating magnetic field and inducing torque, which I'm not going to go into the details of that, but these are based on the common formulas that you had seen before. And then we talked a bit about the power flow inside the machines as a motor or as a generator. So different types of losses, stray mechanical core losses, then copper losses and all of that. And then the definitions associated with voltage regulation, which is for generators, and speed regulation, which is for motors. Okay. Now let's go to synchronous generators. So in synchronous generators, there are basic operational rules. First thing is that you need or require a DC current, which needs to be applied to the rotor windings to create a rotating magnetic field. So you have the rotor, there is DC current embedded on the rotor, and as a generator, you have to provide rotation to the rotor through an external mechanical source. That rotation would create a sinusoidal, basically, pattern of flux changes around basically the circumference of your stator, which will cause sinusoidal voltages and currents to be induced on your generator on its stator. So the prime mover rotates the rotor, inducing a three-phase voltage in the stator windings. Field windings are those which generate the main magnetic field, and they are located on the rotor. So in the synchronous generator, the field winding is on the rotor. The armature winding is where the voltage would be induced, and it would be located on the stator. Rotor types, we discussed that before, salient pole or non-salient pole. Non-salient pole is also called round rotor. The salient pole is usually having 4 or more number of poles. The non-salient pole rotors are usually in 2 to 4 poles. Rotor laminations are used to minimize the eddy current losses. So what was eddy current loss? The eddy current loss was associated with the induced voltages inside basically a magnetic core, which would result in some circulating currents because all magnetic materials are also conductors. So therefore, those induced voltages inside the magnetic materials would cause rotating currents to go inside the magnetic core. So one way to minimize that is to design the magnetic core in a way that they're sliced, but they're sealed from one another so that the electrical currents do not get a chance to go through the whole body of the magnetic core. They just restrict it to their own sheet, if that makes sense. So that would minimize the eddy current losses. Again, about the rotor types, that's the same thing. I'm just showing some pictures in here. This is associated with a round rotor or non-salient, side view, end view, and here we have a salient pole, which, as you can see, the poles are coming out and providing basically a non-uniform air gap between the rotor and the stator. Very simple showing of the rotor, of the round rotor versus the salient pole would be something like this. So in the round rotor, this is the rotor. In the salient pole, this is the rotor. So here is a kind of giving you an idea of what the rotor windings look like, how they are basically wrapped around the rotor, and how in this round rotor versus the salient pole. As you can see here, we have non-uniform distance as the rotor is rotating inside the stator, it would see different, basically, the stator would see different air gaps. But here, the air gap as perceived by the stator or somebody who's sitting on the stator as the rotor is rotating would be kind of fixed or doesn't change. Okay, so we're talking about the ways that we can provide that DC power to the rotor. And if you think about it, that's not going to be a very easy task because the rotor is rotating, and at the same time, you're going to provide some power to it, right? So how would you really do that? So the first or the older method of providing that is through slip rings and brushes, like what we did in the DC machines. If you recall, in the DC machines, we had to fix basically and then rotating parts, as the rotating parts were through the commutation, basically scheme would go through the brushes and commutators. They would their interaction would be in a way that they could provide basically kind of a constant current in a generator action, for example. So the same concept is used in here in the older machines, slip rings and brushes to provide that external, to connect that external DC current source through the rotor. But really in the next generations, there are brushless exciters that are more attractive because these slip rings and brushes have their issues which require maintenance all the time due to wear and tear. But these brushless ones are the ones that are more basically common. So here is basically something that shows you the concept. Here I'm showing on the upper part of this picture, this is schematics, we're showing the rotor. So what is included on the rotor? The lower part is showing what is included in the stator. Stator is where we are fixed, right? Rotor is where we're moving. So, and here in this column-wise, here is this exciter, the rectifier, and the synchronous machine. So the synchronous machine has a rotor part, has a stator part. The rotor part would be here. The stator for the synchronous machine would be here. The rectifier would be located on the rotor. So the rectifier is rotating with the rotor. So the idea here is that you are having an alternating current. You rectify that and feed it to your rotor. How is that possible? That's possible through here on the excitation system. On the stator, you have basically a rectifier where you provide AC source through your rectifier. You get basically a direct current here on the output of your rectifier. This is located on the stator, okay? But since on the rotor, you have a machine which is pretty much an AC machine. This is like a smaller version of an AC generator, which because of the rotational speed of that rotor with respect to the current that is on here on the stator, you have some relative speed. And because of that, there would be wherever I'm showing basically these two circles that are interconnecting with one another, we're showing some induction. Here, induction happens. So because of this induction, you will be producing some AC voltage and current in here. That AC voltage and current would be rectified to give you a direct current, which is on the rotor. That direct current is on the rotor, and that's what we want, right? We provide that rotor current to the field, and here the generation, the actual generation action happens because of the field that is rotating inside the stator. We would get another coupling of voltage in here. So wherever you see these two circles that are kind of overlapping with one another, here's where it's happening. Those are the places where the induction happens. This is like a mini generator. Okay, this is like a mini generator. That mini generator produces an AC current that needs to be rectified and given to your field. This one is on the rotor. This one is on the stator. This is showing a more comprehensive version of this. So this is like a pilot exciter. So if you look at here, this portion is the same that we had in here. Now, the question is how to provide this three-phase input source. Where is it coming from? Where is it coming from? That's important. All right, so this is a self-sustainable system that provides that current for you. So if you look at here, this current is provided through this source is provided through here. So you have a permanent magnet generator. This is a permanent magnet generator. The permanent magnet does not require a field current because the permanent magnets would provide that field. That permanent magnet is on the rotor. On the stator, you have this mini generator, a small generator, is a pilot. It's called the pilot exciter armature. So this is kind of a synchronous machine itself. It provides basically, because of the interaction between the permanent magnet and this winding on the stator, you would have voltage produced in here. This is an AC voltage. This needs to be rectified. So this is the point. This is here is this input source that you have on this figure at this point. You provide the power here. But the good thing about this scheme is that it's self-sustainable. You do not need to provide that external source from another transformer, another generator in the field. What if you have no power? What if you're completely blackout and there's no one to give you any power? Then as long as you have basically a mechanical source in here, that permanent magnet would be able to produce the initial voltage in here to give you the current. And then here you would have your exciter, and then you would have your generator. So it's a little bit complicated, but I've been trying to give you these different basically coupling points so that you get the idea. So it's not as simple as you think it would be. There are a few types of generators that really need to work together to give you the ability of this main generator to produce the voltage for the greater community, if that makes sense, for the network. So this is a pilot exciter. This guy is called a pilot exciter, which is there because it gives you the required basically source when there is nothing in the system, right? When there's nothing in the system, this pilot exciter would provide the required current for this main exciter, which then its current would be rectified to provide the required field for the main generator. The speed of rotation in the synchronous generators is related to frequency and the number of poles. So here is the equation. The frequency that the generator is producing the voltage and current based on would be P, the number of poles, times the rotational speed, the mechanical rotational speed, divided by 120. So through this equation, you can get a sense of what should be the rotational speed of your generator. If you want to have a 60 hertz power in a two-pole machine, then you should rotate at 3600 RPM. If you want to have like a 50 hertz power in a four-pole machine, then you should have 1500 RPM. So you get an idea of how to use this equation in different types of systems in Europe and in the US. The internal generated voltage in the machine is coming from the equations in the past chapter. So this is from the previous chapter. The RMS magnitude of the voltage that was induced in each phase was EA. So this is the RMS armature voltage in each phase, was square root of 2 times pi times NC times phi times F. So what are these? NC was the number of conductors in each phase. Phi was the maximum flux per pole. F was the frequency. So, so it gives you an idea of the fact that the rotational speed, which is determining the frequency, the flux, and some constructional components, this is the number of conductors, is a constructional component, right? So this gives you an idea of this fact that the produced voltage would be determined based on the rotational speed, the flux per pole, maximum flux per pole, and a K, a constant, which is determined by the manufacturing conditions. All right. Based on that, you can get an idea of how the internal generated voltage, which is a voltage on your armature, would be really produced based on what curve. So based on this, you can see that E would be a function of omega and phi. This K is a constant. Since omega in synchronous machines must be constant, you really have one curve that is drawn in your nominal or rated omega. And based off of that, you can relate phi to IF. or EA to IF, because at a synchronous speed, which is the constant rotational speed of the machine. So this plot is called the magnetization curve, or the open circuit characteristic of the machine. This is the voltage that could be measured on the terminal of the generator when there is no load connected, right? When there's no load connected, there would be no current in the armature. So the same voltage that applies on the armature would be really on the terminals of the generator as well, because there's no current in between the armature and your terminal. Now, we want to get an understanding of how the equivalent circuit of your synchronous generator is. We should get basically really a little bit into more the physical phenomena that happen in here. Here, I'm showing basically a rotor that is rotating inside a stator, but the machine is at no load. When the machine is at no load, the only magnetic field that we have in the machine is coming from the exciter, which is on the rotor. So this BR is representing basically the magnetic field that is existing in the machine under no load conditions, right? But here in part B of this picture, we're having a condition where we are connecting our generator to a load, to an external. Because of that external load, there would be some current flowing in your armature, right? So that when the current flows in your armature, it will produce its own magnetic field. So this IA is representing the current that is flowing in your armature. That will produce its own magnetic field. So this BS is representing the magnetic field that has been produced by that armature. And where is that armature located? That's on the stator. That's why we call this BS, the B associated with the stator. So originally, we have the B associated with the rotor, and now we have the B associated with the stator too. Now, this is like an armature reaction, just like what you saw in DC machines. You had an originating magnetic field and another magnetic field that is kind of opposing or reducing the effect of that original magnetic field. So the result would be B net. If you add up these two vectors, you get a B net here. And that B net would be basically proportional to the voltage V phi. And where is this V phi? V phi is the net voltage that you get on the terminals of your generator. So BR would be proportional to the voltage that you get on your armature, but B net would be proportional to the voltage that you get on your terminal. If there is no current in your armature, then B net would go back on BR. They would be the same, right? But if there is a current in your armature, they would be deviated. Based on this phenomenon that I just explained, we have the original vector BR, then IA max is flowing. Because of IA max, we have BS. Because of BR and BS, we have a B net. Now, this B net is determining terminal voltage. BR is determining your armature voltage. Okay, so therefore, you can say that the difference between V phi and EA is associated with some voltage that has been dropped in your armature. And where is your armature? It's in stator. So E stat is representing that component of the voltage that would be dropped in your stator. Now, that voltage is not only resistive, but it's also inductive because we have an alternating current here flowing. This is not like the case that you have in DC machines. In DC machines, the only component in the voltage drop was associated with the resistive component. But here you have both a resistive and a reactive portion. In fact, the resistive portion is very small compared to the reactive portion. So for simplicity, in this figure, we're assuming that there is no resistance. If you're assuming that there is no resistance in the armature, that voltage would be associated with the reactive voltage that has been dropped in your stator. So that explains that JX. So EA is your armature voltage. V phi is your terminal voltage. The difference between these two can be explained by a reactance of JX. And this IA is the current that is flowing in your generator. Now that you understood this concept, we can now add up the components associated with the resistance as well as the component of the leakage reactance, if that makes sense. So your armature winding has a resistance, right? That resistance has an Ra. It will also have a reactive component, some X, which we call it X leakage. Okay, this is extra. This is something else. This is not the same as Jx. This Jx is because of the difference between Br and B net. Okay, but there is another component of reactance that is just a regular leakage reactance of the machine. So I want to bring you to a more advanced version of this equivalent circuit. So this equivalent circuit contained only Jx, but if you add up that leakage component, which is Xa, to that X, that becomes Xs. So this would be the total reactance, which we call it the synchronous reactance of the machine. So keep that in mind. The synchronous reactance of the machine, or Xs, is basically adding these two components together, the leakage and basically the magnetizing impedance in reactance in a way that happened because of this magnetizing effects between the stator and rotor on one another. And on top of that, we also have a resistive component because of the resistances that exist in your armature. That is called Ra. So this gives you a more advanced version of this machine. Here are the three phases associated with the machine. Phase A, B, and C. Each phase has a resistance and a synchronous reactance. Ra is the armature resistance in that particular phase, and Xs is the synchronous reactance associated with that phase. How these three phases work, the whole operation is based on the field current. So if this field current is not existing, there will be no voltage produced in the machine, right? Vf generates If. Vf is provided to your exciter to generate If. So that's why it's also important to acknowledge the existence of this excitation circuit, which is coupled with your armature. All of these equivalent circuits can be explained by this vector diagram as well. So here in your vector diagram, you have your EA. EA phasor is showing the voltage that is produced in your armature. This V phi is showing the voltage on the terminal of your generator here. So EA is here, V phi is here, EA, V phi. There is an angle between these two. This angle is called delta, which we call it the power angle or the torque angle of the machine. So the more this angle is, the more power your generator can produce. All right, so it's really important to understand this. That's why we call it the power or torque angle, because as you play with it, how can you play with that? How can you generate more power? If you give more mechanical power, right? So if you give more mechanical power, you will generate more power. Therefore, the delta becomes bigger. There is a certain relationship between all of these, the mechanical side of the machine and the electric side of the machine. You have to really give that power in order to extract that power on the electrical side. Otherwise, if you just keep the same power on the mechanical side, that power angle will not change, which means that your power will not change on the electric side either. And this IA is representing basically the current in your armature. Now, depending on how your generator is working, whether it's working based on a leading power factor or a lagging power factor, that would be determined by the difference in the angles between V phi and IA, right? And the terminal. The voltage that is on the terminal of your generator versus the current that is flowing in the terminal of the generator. The difference of the angles between these two would determine the power factor of your machine, right? So this is determined by this theta angle in here. Here, with respect to this counterclockwise rotation, are we having a leading power factor or a lagging power factor in this particular diagram? We have a lagging power factor, right? Because your IA lags the voltage. So this IA, once you have it, you can determine how much the resistive portion of the voltage drop in the machine is. That would be RAIA. And you can determine how much the reactive portion of the voltage drop in the machine would be, which becomes JXSIA. Because of J, you have a 90-degree difference, right? J multiplied by XS, that becomes 90 degrees. That's why this angle becomes 90 degrees between RAIA and JXSIA. These two together would determine the total voltage drop in your armature, which determines the difference between V phi and EA, the terminal voltage and the armature voltage. So that's how you can explain the equivalent circuit of the machine and its phasor or vector diagram. Now that you are producing that voltage on the windings of your generators, then you can construct your generator in two fashions. Either you can connect it in Y or in delta, right? So when you connect it in Y, it's as if basically you're connecting the three armature windings in this way. The terminal voltage the terminal voltage here would be related to the phase voltages like this. So you have to add up these two to get the terminal voltage. Or in other words, if your system is balanced, the terminal voltage would be square root of 3 times the phase voltage. Okay. So I recall that sometimes I called this V phi terminal voltage in my previous explanations. I should have said phase voltage really, because this is a more basically, it would be better if I said phase voltage, because those phases, depending on how they're connected, could be the same as the terminal voltage or the phase voltage. Here we see, if you're having your generator connected in delta, then the terminal voltage would be the same as your phase voltage, right? So this is how you can connect your generator in either Y or delta. Now looking at the power and torque, the way that power flows in your synchronous generator, on the input side, you're providing some torque, applied torque to the machine. You have some rotational speed. When you multiply these two together, that becomes the P input on the mechanical side. Now, stray losses, friction and windage losses, core losses, they would be all subtracted from that mechanical power to give you the converted power. That converted power is the power that is existing kind of in the air gap of your machine. And then once you subtract the copper losses from that, that would be the power that would be delivered to your system, or the output power. Now, if you look at that output power can be always expressed in terms of the terminal voltage and the line current. Square root of 3 times of Vt times IL times cosine of theta, that becomes the output power, the three-phase output power. And what is that theta? That theta is the angle between V phase and IA. Remember, that's the angle between V phase and IL. You can also show the output power in terms of the phase voltage rather than the terminal voltage. So the output voltage in that sense would be 3 times of the V phase IA cosine of theta. And that IA versus IL is the line current versus armature current. So look at here. In the Y-connected case, the armature current would be the same as the line current, right? But in the delta case, no. The line current is not the same as the armature current. Armature current is within that triangle. On the contrary, the terminal voltage would be the same as the phase voltage in the delta connection, but here in the Y connection, the terminal voltage would not be the same as the terminal voltage would not be the same as the phase voltage in the Y connection. So keep that in mind. And the reactive power could also be defined based on the same concept. The only difference is that you need to put sine of theta instead of cosine of theta to find that out. The converted power is the power that is existing here in the air gap. So the difference between the converted power and the input power is in the difference between the mechanical torque versus the electromagnetic torque. So this tau induced is also called electromagnetic torque. That's on the electromagnetic side of the system. This applied torque is also called the mechanical torque, which is on the mechanical side. The difference between the P in and P converted would lie in the difference between these two torques. And for the P converted, you can find it from tau induced times omega m, which would be really 3 times of EA times IA times cosine of gamma. And what is that gamma? That gamma is the angle difference between EA and IA, which is the same as delta plus theta, the power angle plus the power factor angle. So remember, there is a major difference between theta and delta. Delta is called the power angle or torque angle, but theta is called the power factor angle, right? The power factor angle is mostly associated with the electrical side of the system, the difference of angles between voltage and current. But its power angle lies really basically on the mechanical side of the system, because that is the one which can determine how much power you can provide to your system. So we talked about the basic operation, rotor types, including the salient pole and round rotor. And then we talked about how the exciter works. So we could have a pilot exciter, and the synchronous generator all basically in the same station in order to be able to run the generator when the system is starting from a blackout. And then we talked about the relationship between the number of poles and basically the frequency of the system. And also we talked about how much voltage is going to be induced in the armature, and the curve associated with the internal generated voltage under no load conditions. And then we talked about the equivalent circuit and how basically the armature current could impact the voltage that is induced in the machine in the form of the phase voltage that is going to be induced on the system, how it's going to be different from the internal voltage. And we talked about the three phases and the vector diagram, and then the three phases, how they could be interconnected with one another in the forms of basically Y and delta. And we talked about power and torque, the flow of power, also P converted, and its relationship with the phase voltage and internal voltage, as well as the induced torque. Okay, now let's go over measuring the synchronous generator characteristics. So these are the components that we need to be able to find out through measurements inside the lab. So these are basically XS, the synchronous reactance of the generator, EA, which is the internal voltage, and RA, which is the basically armature resistance. In many circumstances, RA can be ignored because it's very small, but even if it cannot be ignored, we can basically go ahead and measure that. So step one would be to do an open circuit test. In the open circuit test, we open basically the terminal, and then we run the generator at the rated speed. And then we are going to increase the field current until the terminal voltage, and basically measure the terminal voltage as we are gradually increasing the field current. Since there is no current in the machine, the terminal voltage would be equal to the terminal voltage over here would be equal to the internal voltage. Therefore, we can plot basically EA versus the field current. So EA or VT, terminal voltage, when there is no load in the machine, versus current can be basically plotted. This shows the OCC, or open circuit characteristic of the machine, which has a linear region when the machine has not gone into saturation. And then the linear part is also called the air gap line. So this is pretty much a straight line. But after a certain point, you see that you go into saturation. So the characteristic will not be linear anymore. Then step two would be to do a short circuit test. Once we do the short circuit test, it means that we need to close the generator terminals. We need to short it. And then we're going to increase the field current such that basically we can measure the armature current. So this is going to produce the short circuit characteristic. So we are going to measure IA, or the armature current, versus IF, which is the excitation current. Typically, this is a straight line because the machine doesn't go into saturation in this case. And we can see that IA can be measured by dividing EA over RA plus JXS. Okay, so again, a recap. Step one, open circuit test. Step two, short circuit test. Now, how we are going to find out the different parameters. Firstly, the armature resistance, if it cannot be ignored, we're going to apply a DC voltage to stator while the machine is stationary. So this is a DC test. We're going to measure the current to calculate the resistance RA. So this is only an approximation, since the AC resistance is typically greater than the DC resistance due to skin effect. But it gives us a good approximation of what the RA would be. So this is through basically a DC test by applying a DC voltage to stator. while it is not rotating. And then in order to find out the reactance, the synchronous reactance XS, we're going to get the EA from the open circuit test for a given field current. We're going to get the IA from the short circuit test at the same field current. And then we're going to use this ZS is going to be EA over IA. So here at a certain basically IF, we're going to see how much voltage we have. At the same current, we're going to see how much IA we have. And then we divide these on one another. That becomes the synchronous basically impedance. And since synchronous impedance is RA squared plus XS squared, and we already measured RA from the test, the DC test that we had, then we can find out XS. Okay, so this is how we can measure the different characteristics or parameters associated with our generator. We need to understand a few notes here. Note one is that these tests are only accurate under linear region of the OCC, under unsaturated region. So therefore, we need to pay attention to the fact that we should work around the unsaturated region, find the IF voltage and IA associated with the IF that has not taken the machine into saturation. And then note two is that in many circumstances, if we ignore RA, then we can approximate XS from EA over RA. And then we have a definition that is called the short circuit ratio. The short circuit ratio is defined as the ratio of the field current required for the rated voltage at open circuit to the field current required for the rated armature current at short circuit. So if you pay attention to this definition, you see that the short circuit ratio is the same as the reciprocal of the synchronous reactance almost. So this is an important, basically, definition, short circuit ratio. Usually, it talks about how strong a synchronous machine is. So in other words, if you have a high SCR short circuit ratio in a system in general, you can say that that's a stronger basically generator that can result in higher short circuit currents if shorted. And it's usually the indication of a strong system in general when we're talking about the bulk generation transmission systems. So we like to have basically at substations, different substations in our system, we like to have higher SCR. If we have low SCR, low short circuit ratio, this is usually an indication of a weak power system. All right, so let's look at this example 5.1. Example 5.1 is talking about a 200 kVA, 480 volts, 50 hertz, Y-connected synchronous generator with a rated field current of 5 amps. And the following data have been taken using that 5 amp test. We're going to find out the VTOC, or the terminal voltage under open circuit conditions, at the rated IF, to be measured at 540 volts, and IL under short circuit conditions at the same rated IF has been found at 300 amps. So this is coming from at a certain IF. We're measuring basically from the open circuit. We're measuring VTOC to be 540 volts and IL short circuit to be at 300 amps. And also, when we're applying a DC voltage of 10 volts to the two terminals of the generator, a current of 25 amps has been measured. All right, so we want to find out the values of the armature resistance, approximate synchronous reactance in the ohms. Basically, through the DC test, since the machine is Y-connected, we can say that in the DC test, we've been applying a voltage to the machine in the Y-connected machine, basically. So this is the Y-connected machine. This is the terminal voltage. And we've been applying a DC voltage. So therefore, under these circumstances, what we measure would be 2 times. So BDC over IA would be 2 times of RDC. Okay, keep that in mind, since this is a star-connected generator. If the generator was not star-connected, then how would we do this? How would we find out the RA? So under these circumstances, we need to pay attention to the fact that this is going to be our test now. We're going to basically apply the DC voltage here. So we have one R here, 1 R here, 1 R here. So therefore, the current that we measure, so VDC over IA should be equal to R in parallel with 2R, right? So from here, we can find out the R. All right, so here, since we are Y-connected, we can find out, or we can measure our A to be at 0.2. And then at the same IFs, we found basically 540 and 300. And since the machine is, again, Y-connected, we need to pay attention to the fact that this 540 needs to be divided by square root of 3 to find out the open circuit phase, basically, voltage. So the open circuit phase voltage is 311.8. And then since the machine is Y-connected, the armature current would be the same as the line current, equal to 300 amps. So then we are going to divide these on one another, 311.8 over 300. That becomes the square root of basically RA squared plus XS squared. So from here, you can find out XS to be equal to 1.02 ohms. Now, if you ignored RA, then XS would have been found by directly measuring the EA over IA, which becomes 1.04. So if you compare basically the results here, you can see that the error is very small due to neglecting the RA in the machine. So this is just an example to show you how we can find out the different parameters of our generator using the short circuit and open circuit tests. Let's talk about the synchronous generator when it is operating alone. So single generator operation. The effects of load change would be that by adding the load, the real and a reactive power, whether the real portion of the load or reactive portion of the load, we're going to increase the load current, which means that generally speaking, we can impact the voltage on the terminal. So by adding load, we would be basically changing the phase voltage. So this is basically how this is going to happen under different power factor conditions. When you have a lagging power factor, so V phi here is the original phase voltage on the terminals. Then if you have IA, the current of the armature, then you can see that you would need to add V phi to JXSIA through the KVL in the machine to find out EA. So this would be your EA. Now, if you're trying to keep EA at the same value, so how would you be able to keep EA at the same value? EA is the internal voltage. The internal voltage of the machine would be kept constant if basically phi is constant and if omega is constant, right? Omega is constant in the synchronous generator at the rated value. And this means that if you keep phi to be constant, which means that you do not change the internal voltage, then E prime, when you're increasing the load's current from IA to IA prime, you can see that IA prime is a bigger value, then you will see that generally speaking, V phi prime would be smaller under lagging power factor conditions. So this is what happens when the nature of your load is RL, combination of resistance and inductance, then as you're increasing your load, as the current in the machine increases, you get a voltage drop in the terminal voltage. All right, so this is a deep, basically sharp or deep, basically decrease in the voltage. When you have unity power factor, you pretty much have the same effect, except that it's not as sharp as the case for the lagging power factor. So for the unity power factor, you generally are decreasing the voltage on the terminal of the machine, but slightly. Now, under leading power factors, on the contrary, we would be generally increasing the terminal voltage. So the terminal voltage would be increasing in this case. Why is that happening? That's due to the fact that basically under leading power factor conditions, we are not consuming reactive power really from the machine, but we are injecting reactive power into the machine. So that's a major difference between the two cases. Under leading power factor, you're getting P from the machine, but you are injecting P into the machine, leading power factor. So under these circumstances, your voltage increases. The terminal voltage will increase. All right, now we're going to show this phenomenon through a definition called voltage regulation. So voltage regulation is defined as the no load voltage minus the full load voltage over the full load voltage times 100 to describe that in percent. Under lagging power factor and unity power factor, usually what we have is basically a positive voltage regulation. But under leading power factor conditions, we get a negative voltage regulation. So keep that in mind. Now, how do we basically counteract the effect of voltage drop? If the voltage is dropped on the terminal, then we usually need to basically increase IF, the excitation current, in order to increase the magnetic flux. By increasing the magnetic flux, we're going to increase the internal voltage. And since if we are increasing the internal voltage, then the terminal voltage also will raise. So that's the counteraction when you want to have a control over the terminal voltage of your generator. In example 5.2, we have a 480 volts, 60 hertz, delta-connected 4-pole synchronous generator, which has the OCC, open circuit characteristic curve, as shown in this figure. The generator has a synchronous reactance of 0.1 ohms and armature resistance of 0.015 ohm. At full load, the machine will be supplying 1200 amps at 0.8 lagging power factor. Under full load conditions, the friction and windage losses are 40 kilowatts, and the core losses are 30 kilowatts. We want to ignore basically filled circuit losses. What is the speed of rotation of the generator? That's the first question. Okay, so the speed of rotation in the generator, contrary to what you had in DC machines, you remember that in the DC machines, the rotational speed of the generator could be varying a lot under different load conditions. But in synchronous generators, the name synchronous generator shows that if under basically steady state conditions, the rotational speed of the generator must remain constant and must be basically proportional to the frequency of the system. How? Through basically this relationship. So F, the frequency, must be equal to the P times Nm over 120, or in other words, Nm, the rotational speed of the generator, should be 120 times F over P. Since we have a 60 hertz basically machine and 4 poles, then this indicates that under steady state conditions, our rotational speed in the generator must be 1800 RPM. So this is the answer to the first part of the question. All right, in part B, it's asking how much field current must be supplied to the generator to make the terminal voltage 480 volts at no load. How much field current must be supplied to the generator to make the terminal voltage 480 volts at no load. So since there is no load in the machine, the terminal voltage would be the same as basically the internal voltage of the machine, right? So in this machine, VT would be equal to V phase. That's because we are delta connected. Since the generator at no load has a 0 armature current and EA is equal to V phi, therefore VT would be equal to V phi would be equal to EA. All of them would be equal to 480 volts. And from the open circuit characteristics, this IF should be found at 4.5 amps, right? So go ahead and look at 4.5 through the characteristic, and you would read the voltage here, which is the same as the open circuit voltage, and you get the 480 volts. So, or go ahead and look at 480 and then read basically the corresponding IF. That would be equal to 4.5 amps. So this is the answer to the second part of the question. Third part, part C, is asking if the generator is now connected to a load and the load is drawing 1200 amps at 0.8 power factor lagging, right? Then how much field current will be required to keep the voltage equal to 400, the terminal voltage equal to 480 volts, okay? So we start from the terminal voltage. There is a relationship between the terminal voltage and the V phi and also the internal voltage, EA. If the generator is supplying 1200 amps, keep that in mind, since the machine is delta connected, then you have to divide 1200 over square root of 3 to find out basically the current inside the armature. So the armature current would be found at 692.8. And the phasor diagram has been shown in figure 523b. Now, under these circumstances, you can find out EA, the internal voltage, using 480, assuming that the phase voltage, in one of the phases, usually phase A standing for the reference of angle for us, then this gives us basically this angle is associated with a 0.8 lagging power factor. And through this equation, you can find out the internal voltage to be at 532 with angle 5.3 degrees. So therefore, now you have to, again, go back to this open circuit characteristic, go over the 532, and read the associated IF. If you do so, you will see that the field current must be equal to 5.7. Okay, that's the answer to part C. Next part is asking how much power is this generator supplying? How much power is supplied to the generator by the prime mover? What is this machine's overall free efficiency? Okay, so how much power are we providing through the terminals? That would be square root of 3 times VT IL cosine of theta, and that would give us 798 kilowatts. To determine the efficiency, we need to find out basically how much power is provided to the machine on the mechanical side from the prime mover. And that would be equal to the output power that we just found, plus the losses, whatever loss we have in between. The stray losses have not been specified, so they will be ignored. However, you can calculate the losses in your armature. And core losses was approximated by the problem statement at 30 kilowatt. Friction and windage losses were around 440 kilowatts. So therefore, you add up these values to P out to find out P in. And this can give you the overall efficiency of the machine to be at 89.75%. Now in part E, it's asking if the generator's load were suddenly disconnected from the line, what would happen to its terminal voltage? So if the generator's load were suddenly disconnected, the current would be 0, the current in the generator, making EA to be equal to V5. Since the field current has not changed, so remember, there is no discussion of change in the field system. So field system is still the same. So therefore, EA will not change. V5 and VT must also rise, therefore, to be equal to EA. Therefore, if the load were suddenly dropped, the terminal voltage of the generator would rise to 532 volts, which would be corresponding to this EA, the internal voltage that has not changed. And then finally, suppose the generator is connected to a load which is drawing 1200 amps at 0.8 power factor leading. How much field current would be required to keep the voltage at 480 volts? So here, that's basically going to be compared with part C. In part C, we had the 0.8 power factor lagging. However, in part F, we have the leading power factor, which means that we would require less in general IF or excitation current. Let's look at this. The calculations associated with this angle now, plus 336.87, would give us basically the internal voltage to be at 451. And you can compare that with 532 in part C when you had lagging power factor. So generally speaking, with the leading power factor, you require less. Therefore, if you go ahead and look at the open circuit characteristic of the machine, go to 451, and then you can read basically the IF to be at 4.1 amps, which is a smaller current compared to 5.7 here. So which type of load, leading or lagging, would require a larger field current? The answer is that the lagging power factor would require more field current to provide the same terminal voltage. Example 5.3, we have a 480 volts, 50 hertz, Y-connected 6-pole generator, synchronous generator, which has a per phase synchronous reactance of 1 ohm, and its full load armature current is 60 amp at 0.8 power factor lagging. This generator has friction and windage losses of 1.5 kilowatts and core losses of 1 kilowatt at 60 hertz at full load. Since the armature resistance is being ignored, we assume that Ri squared losses are negligible. The field current has been adjusted so that the terminal voltage is 480 volt at no load. So here are the questions. Part 1, what is the speed of the rotation? Speed of the rotation in part A is constant, equal to 1,000 RPM, using basically this relationship. Part B, what is the terminal voltage of the generator if the following are true? When the machine is loaded with the rated current, and the rated current is how much? It's been indicated here, 60 amps. At 0.8 lagging power factor, at unity power factor, and at 0.8 leading power factor. So This is similar to the previous problem. I'm just going to look at basically the voltage drop associated with the armature in each case, and then you can find that in part one, the terminal voltage is 410 volts. In part one, when there was a lagging power factor of 0.8. And then in part two, when we have unity power factor, the terminal voltage would be 468.4. Part three, when you have leading power factor, the terminal voltage would increase to 535. And this is what we expect. As you have a leading power factor, usually it means that the terminal voltage should be going higher. So compare that, starting from the lagging 410 to unity 468 to leading 535. It's going to increase the terminal voltage. Part C is talking about the efficiency of this generator. We're ignoring the copper losses, and we're considering the 0.8 power factor lagging condition. So in order to do this, we find a P out, then we find a P in, we find the efficiency from P out over P in, which would be 93.2%. Then part D of the problem is asking about the shaft torque by the prime mover at full load. So P in would be tau applied times omega m. Therefore, tau applied would be P in, which we found here, over omega m, which would be 349.6 Newton meter. If you have the fourth edition of the book, I believe there is basically a mistake in the text. So this should be the correct answer. This 104.7, the mechanical basically speed of the machine, is what we found in part A here. So we should apply the same value. And P converted would be basically equal to, this should be not tau applied, this should be tau induced. So this is also incorrect. So make sure you correct that. So from here, you can find out that the P is 325.7 Newton meters. Now it's talking about the voltage regulation in part E at 0.8 power factor lagging in these three basically cases when you had lagging, unity, and leading power factors. So using the voltage regulation, in the lagging case, you have positive voltage regulation. In the unity power factor case, you have, again, positive, slightly small, smaller, much more smaller than the lagging case. And under the leading power factor conditions, the voltage regulation is found to be negative. So this is expected based on what we discussed in here. Under different power factor conditions, what we would expect as the voltage regulation. Okay, now let's go to example 5.4. We have the same machine as in example 5.3. So this is example 5.3 statement, which is operating at no load with a terminal voltage of 480 volts. We want to plot the terminal characteristics, the terminal voltage versus the line current of this generator, as its armature current varies from no load to full load conditions at lagging power factor case of 0.8 and leading power factor case of 0.8. We want to assume that the field current remains constant at all times. So we're not making any changes in the field circuit. So this is an extension to the previous problem that you had. So in the previous problem, you found in each of these lagging or leading power factor cases, you found basically the voltage. So we're going to repeat the same process under different armature currents. So when you're adding, basically, when you're changing the armature current from, for example, 0 up to all the way up 60, which is the full load armature current, at the same minus 33.87, which is corresponding to 0.8 lagging power factor, then you can recalculate these VT at different armature currents. Same way for the leading power factor case. The only difference is that you would need to put the plus 36.87 degrees. And when you repeat that, you will see that under basically the lagging power factor case, as you're increasing the line current, the terminal voltage will decrease. However, in the leading power factor case, you see that as the line current is increasing, the terminal voltage also will increase. And this is based on the discussion that we had. Okay, now let's look at parallel operation. When we're connected with the grid, there are multiple thousand number of generators that are all interconnected with one another through the power system to provide us with the required power. So it's important to understand how parallel operation in these generators work and how we can basically put a new generator in parallel with the rest of the generators in the system and what are the conditions associated with that and so on. So why parallel operation? Because multiple generators can collectively supply a larger load. It will increase the system reliability because failure of one generator will not cause the total power loss in the system anymore. It will allow for maintenance by taking individual generators offline without interrupting the supply. So you can take one generator out and put another generator in for maintenance, basically, purposes. It will improve the efficiency because smaller generators can basically come into picture near their full load conditions, which would basically provide more efficiency rather than working a single large generator under loaded conditions, which increases the losses under these circumstances. So in other words, you can come up with the best combination of the generators in the system that could provide the most economical scenario for powering your loads in your system. So these are some of the advantages associated with parallel operation of synchronous generators. Now, what are the conditions associated with paralleling the generators? We have to make sure that we have equal RMS line voltage between both generators. So suppose that you have one generator already in, you want to add another generator. You need to make sure that the RMS line voltage of the new generator is the same as the basically generator or the generators that are already connected with the system. You also need to have the same phase sequence. So this is important to basically understand. So we have usually the ABC is the standard phase sequence, which means that with respect to counterclockwise rotation, voltage in phase B would be behind the voltage in phase A by 120 degrees, and phase C would be 120 degrees ahead of the A. This is the standard ABC phase sequence. However, there might be a case where the newer generator has an ACB phase sequence, which means that with respect to the counterclockwise rotation, voltage in phase C is now behind voltage in phase A, and voltage in phase B is ahead of voltage in phase A. So under these circumstances, we need to basically pay attention. We should not put these generators in parallel with one another because that results in a lot of basically stress between the two generators, which could cause basically a failure and the outage. So that should be avoided. So we have to have the same phase sequence. All the generators either need to be ABC or ACB. Also, the phase angles for the corresponding phases must be also equal. So we need to make sure that the voltage angles are also equal when we are making them in parallel. And also, the last condition is that the oncoming generator, the generator that is new and wants to come in, needs to have a slightly higher frequency, a little bit higher than the frequency of the rest of the generators when we are going to connect that with the system. That's because basically under these circumstances, we make sure that the new generator will adapt to the common basically frequency of all the other generators without any interrupt or without any failure. If the frequency of the oncoming generator is below the rest of the generators, this will cause a motoring action. So there would be some power flow from the rest of the generators towards basically the new generator that is coming into the circuit, and it causes it to act like a motor. There would be a reversal of the power. So usually generators have relays that avoid basically the reversal of the power. That does not allow the system to come into circuit, and it can cause some other failures as well. So we need to make sure that we follow all of these conditions. Not meeting these can cause damage in current surges or power transients. So make sure that we pay attention to all of these. The procedure for paralleling, we need to be able to match the terminal voltages using a voltmeter. We need to confirm the phase sequence. So usually a 3-bulb method is used for this purpose. We need to adjust the oncoming generator's frequency slightly higher than the system. We need to observe the phase angle of the upcoming generator for light bulbs, and then we can close the switch when the voltages are in phase. So here are some of the synchronization tools that can help us with that. Here, the 3 light bulb is when this generator number 2 is going to be connected with generator number 1, for example. At first, these breakers are open. However, there are some 3 lamps between basically these 2 points. Now, if these 2 generators are really in phase, it means that the voltage of phase A for generator number 1 with respect to phase A of generator number 2, they do not have any phase difference. And their voltages are also equal, right? So this means that this lamp should be turned off or needs to be dimmed under the right time when we want to close the switch. Same thing for the other 2 phases. So if this is phase B, really at the time that we want to close the switch, this light bulb should be dimmed. And the same for phase C. Now, if there is a difference between the phase sequences, you never get a condition when all of these 3 light bulbs would be dimming at the same time. So that could be an indication of the out of sequence, basically, a condition between the 2 generators. So if the 2 generators have the same phase sequence and are synchronized, then at some point in time, the 3 lamps will dim, which means that it's safe to switch the oncoming generator at that time. So this is the 3 light bulbs method. There is another tool that can help us with the synchronization, and that's called the synchronoscope. So synchronoscope is usually basically showing the angle difference between the 2 generators in the same phase, usually phase A. So when there is no phase shift between the 2 generators, we would be at this point, basically 0 phase shift. When we are slightly to the right, it means that it's safe to basically close the switch when we're towards the right side, towards the basically clockwise. So usually that's an indication of being able to close the switch at that time. However, the synchronoscope is not by itself does not show that the phase sequences of the 2 generators are the same. So again, depending on different tools that we have in hand, we need to make sure that the sequence of the generators are the same and the phase angle difference between corresponding phases are minimal when you are going to switch on the newer generator with the rest of the system.